We'd like to welcome you to another in a series of webinars designed for departments of transportation. I'm Terry Bills, and I'm the Transportation Industry Manager here at Esri. And today I'm joined by a full contingent of colleagues from Esri. We have Kurt Schwope, Mark Romero, Brian Connolly, Sarah Black, and Amin Tayebi. And so we have a lot of great things we want to show you today. So today we're addressing LiDAR imagery and imagery management and a whole host of the full platform, if you will. And while imagery can come from a number of different sources, whether satellite, aerial, or UAVs, the goal for today is to introduce how you can develop really an enterprise strategy for managing your agency's imagery data and discover ways in which you can drive performance improvements in your organization. I'd like to point out that we're recording this webinar, and while everyone will be on mute, there will be time for question and answers at the end of the presentation. So you can type your questions into the question box. We'll try to answer as many as time allows. And additionally, the slides, which are part of this webinar today, will be available to you on the GeoNet group, Departments of Transportation. And we'll give you that link at the end of the webinar. So, all right, let's start with the simple observation that just about any department in a DOT can use imagery data, and that LiDAR and imagery information has become an integral part of a large number of our standard workflows in DOTs, whether we're doing initial project planning, project design work, conducting inspections, or doing maintenance in the field. Having a digital view of background information can really help provide context and greater validation of your business and GIS information. And while we may all agree on that, unfortunately, many agencies struggle with how to manage their imagery in a comprehensive way, with the result that often different departments not only manage their own imagery data, but often have separate procurements for their own data independently from others. And another common problem is that given the scale and size of various imagery data, many agencies struggle with managing the large volumes of data, with the result that few outside of a small group are able to access imagery data that may already be held in their own organizations. So I think there's really maybe four main issues, that common themes that most DOTs must address with respect to imagery data. And first is really how to achieve a comprehensive and efficient way of delivering imagery information to your organization without creating duplication and redundancy. And that raises the second issue, which is really revolves around the size of some of these data sets. So I'm talking about LiDAR data for an entire state highway system. I'm really talking about a great deal of information. So how do I manage that? How do I make it easily accessible to people who need access to that information? And I think that's where many agencies are increasingly looking to the cloud, and we'll discuss that as well. And third set of questions relates to the fact that often I may have several iterations or time periods of imagery data. How do I manage that, and how do I make it easy for my users to be able to compare information over time? And finally, the use of LiDAR data within DOTs has, we've seen, really exploded over the last 5 to 10 years. And the ability to extract and analyze key features from that LiDAR data for asset inventories, and how LiDAR can be used for precise measurement, really almost equivalent to traditional survey techniques. But rather than having me go on about that, let me turn it over to Kurt, and let's kind of see what they have prepared. So Kurt, over to you.
Great, thanks, Terry. Let me go ahead and bring my screen up here. Hopefully everybody can see it. Anyway, welcome to our webinar today. about the ArcGIS imagery and LiDAR platform. Today's presentation is going to be covered at a pretty high level because we have a short amount of time, but I want to encourage each of you, if you see something that interests you, just reach out to us. We'll be happy to meet with you directly and do a deep dive into some of these more specific capabilities in more detail. So I'd like to introduce our speakers for today. Sarah is actually an imagery scientist. She's a solutions engineer on the imagery team. Sarah is going to be talking about imagery analysis. Mark Romero is our imagery team lead solutions engineer. He's going to be showing some of the new capabilities with regards to our enterprise drone to map solution. Brian Connolly is a solutions engineer on our imagery team who's going to be talking about LiDAR. And then wrapping up the presentation is going to be Mean Tayebi, data scientist, and he is on the Esri artificial intelligence team. And he's doing some very exciting work with extraction of features from LiDAR data. So our ability to collect information about the world is rapidly expanding. It seems like every week a new satellite or a drone company is being launched, but we know that GIS provides this modern framework for managing geospatial information. Fortunately, it can do the same with remotely sensed imagery. ArcGIS provides a very robust imagery management capability that supports your authoritative system of record. It also has a large amount of raster analytics, image processing. This is your system of insight. It's converting that imagery, that raw imagery content, into usable information. And then finally, the system of engagement. That comes down to imagery services, where we can take all the derived products plus the raw content and then share that across the organization using some of the more advanced imagery services capabilities that the platform provides. Since I joined Esri about 8 years ago, I've seen significant changes in the capabilities of our platform. We've reached the point where it truly is a comprehensive image processing solution that I feel can readily support the needs of just about any DOT or any other state agency for that matter. But the most important thing to kind of remember about where imagery starts at Esri is with ArcGIS Pro. I hope that many of you have started to switch over to Pro from desktop because it is obviously more and more becoming the solution for imagery. Pro is superior to ArcMap because it was designed from the bottom up to work with imagery. Desktop just did not have the processing muscle or graphics capability to work with imagery quickly or efficiently. In the first place, ArcMap can only display imagery in map coordinate space. So if you look at this oblique imagery, you'll see those buildings are leaning off to the side. Well, with the click of a button in Pro, you can now switch that image, if it's taken obliquely, from map coordinate space into image coordinate space. So now the imagery looks exactly the way the sensor took the image, but the system maintains all the geospatial referencing. So your feature layers, your vector features perfectly fit over the top of that oblique imagery. And to achieve that, we've had to implement photogrammetry within the package. So we have to understand the sensor models that's collecting the data. And that opens up a whole new way of doing different types of mensuration. So, in the past, you've been able to measure areas and lengths and distances and those types of things. Now we can actually go into a 3D oblique image and we can, actually measure the heights and those types of things because we understand the photogrammetry that's behind the imagery. We also provide a number of visualization capabilities. So in this case, we're looking at our base map, but we brought in drone imagery, very high resolution drone imagery, and we can swipe back and forth on the top of it, and then we can do some analysis and some feature extraction from it. So in this particular case, we were looking at a rail yard. We brought in our high resolution drone imagery, and then we started mapping out where the different frogs, the switches, and those types of things that make up the assets within the rail yard. And then to bring it all together, we put an operations dashboard behind it. And so in real time, as you bring your imagery in, you can have your analyst kind of editing and looking at the different data. And then it's constantly updating that information to the decision makers using some type of story map or operational dashboard approach. What's really important is right now, this is a little bit of a manual process, but as we get more and more further along of automated feature extraction and AI, this will be done dynamically on the fly and just populating those dashboards. And we're going to talk a little bit about that on how you extract features out of the imagery. We're going to go in and show an example of how we can just take standard aerial photography, 4-band imagery, RGB plus a color infrared band, and use that to actually map and extract land cover and calculate the impervious surfaces. So if you have a stormwater management project where you're trying to calculate drainage, this is the type of thing that you can use to calculate your land cover and do that impervious surface analysis. And of course, once you get those techniques down on extracting imagery, you can start applying it to a whole bunch of other applications. Sarah's going to talk about that in the presentation. We're also going to cover feature extraction from land cover from the standpoint of AI. And you'll see, and Amin's going to talk about this, we have a number of new capabilities inside of ArcGIS Pro, and then how it applies into our Raster analytics capability to actually use AI to train up the system and do the extraction of features using machine learning, machine vision, and AI techniques. So Amin's going to talk about that. And not only are we doing this with raster imagery, but Amin is actually pulling features out of point clouds collected by terrestrial LiDAR systems. So it's very exciting what we're able to do there. As Terry was talking, the heart and soul of this whole capability revolves around imagery management, because you start dealing with lots of images that you have to work with, you have to access. The key thing, and kind of a different way that we've approached our imagery management is that we aren't concerned about files. So the Mosaic data set is this data model that we have for imagery that will tell our image server exactly where your files are, but more importantly, where the pixels are for each one of those files. So as you start working with images, you don't go in and say, open this file or open this file. You just draw your bounding box on your map and say, I'm interested in this area. And the system will use the Mosaic data set in the image server to automatically go out and pull in the pixels that you want to process and you want to work with. So you're not working with files, you're worried about areas of interest. And we can do that same thing now with point clouds. So it's really exciting on how that whole management of remotely sensed content is working. And we work very hard to keep the Mosaic data set and those capabilities up to speed. So we can access all types of imagery, whether it be collected by satellite, aircraft, or of course, drones now seems to be the biggest growth area that we have for remotely sensed content. And of course, we talked about services and the importance of services. Those services then can be used by our desktop applications like Pro. So you can access the services, bring it in, do exploitation against it. We're starting to build a number of web apps that can take advantage of that. And then of course, our story maps and our operations dashboards that you can build through ArcGIS Online can also fully take advantage of these imagery services. Switching gears a little bit, we have focused very heavily the past year or so on photogrammetry, as I mentioned before, specifically within regards to drones. This is an example case of one of our customers in Virginia, Will Shewart. He actually went out and he collected this airfield. 4,800 images comprise the collection, and he used our drone to map solution to come in and create this 3D visualization of this airfield in southwestern Georgia. Southwestern Virginia. They're talking about expanding this airfield, and so they needed some visualization products to really get a good understanding of how that would work. And Will was able to do the collection and all the processing to make these products in just 3 days of operations. And a little bit later, Mark's going to talk about our newest capability. Many of you probably heard of Drone to Map and its ability to be a standalone solution that can actually come in using a PC and process your drone imagery photogrammetrically. We now have a new enterprise UAS solution that we call, it's going to be a SaaS offering. It's called Drone to Map for Enterprise, and it includes very powerful capabilities like advanced flight management, allow you to set up your collection patterns for your drones. It includes elastic processing, so the more images that you throw on it, the more systems it'll actually spin up and start processing the data. We've improved the mesh capabilities on this thing so it can get very high resolution detailed 3D meshes. We actually use the recap capability that's associated with Autodesk to do those meshes. And of course, all the output products are compatible with your all the various apps that we have on the ArcGIS platform. And like I said, Mark is going to show that process here in a little bit. Another exciting capability we have is starting to work more and more with point clouds. Brian Connolly is going to give a good presentation on how we work and extract, both manage and extract features out of LiDAR point clouds. But I just want to show this video that was put together from one of our partners, Regal. Regal is a sensor manufacturer. They make a number of different both airborne and terrestrial LiDARs. And they put together this solution called LMAP, which is basically a LiDAR management system similar to the Mosaic dataset that we can use to actually go in and manage massive archives of LiDAR point cloud imagery, and then bring those in, do searches and queries, bring them in, and then do the visualization. And right now we're just looking at a thin client that is able to go in and create and look at a scene layer package that's associated with each one of those LiDAR tile formats. And we're able to bring that in and do basic type of exploitation with it. So in this particular case, we're just measuring the height of an overpass on this imagery. This is I guess a project that they were doing for the Florida Turnpike group. But you can see, once again, these different queries going in and finding your content wherever it might be in the world. And so now they've switched to this other location. This is actually an area collected over Europe. But you can see now from a visualization standpoint, we're doing things like looking at both the DSM and the DEM. So we have the bare earth that we actually created from the LiDAR, and we have the DSM over the top of it. And we can swipe and compare it. And then in this final application, you see off to the left, that's your data management. We maintain all the metadata about each of the files, and we can access the reports. But now we're looking actually at a rail corridor, point clouds. And very similar to kind of the overpass that we had with the Florida Turnpike, here's an overpass that we have with a rail application. You can just see the level of detail. Now, this particular LiDAR was collected from a laser scanner mounted on a rail car. And so you can see the level of detail that was collected. But this is even more significant in that we can also visualize something like a tunnel. So I just made the top base map layer transparent, and now I just dove down into it, and I'm actually visualizing a tunnel underneath the waterway in the point cloud. And this is all virtual, and Brian's going to show this in a little bit more detail as he goes through his demo. So before I turn the presentation over for the demos itself, let's just take a final look at this kind of complete platform, if you will. So we have the ability using the Mosaic dataset to basically bring in all types of imagery. As I said, whether those come in from satellite, from aircraft, from drones, or now, of course, a big push on these terrestrial laser scanners. We can bring that in. We can organize that data using our Mosaic data sets in the image server. If we need to correct that information, if we need to make it more accurate, or we need to extract 3D information from stereo imagery, we can use the new photogrammetric capabilities of Drone to Map in our new Ortho Maker software to do that ortho photogrammetry and DEM extraction. And of course, we can also run the analytics, the feature extraction, and then serve that up all inside of Pro and Excalibur, which is one of our thin client applications. So it's very exciting. It's a complete, robust platform that allows this end-to-end processing of this imagery data. So that includes just kind of a brief introduction. I'm now going to turn it over to Sarah Black, who's going to talk about using some of the Raster analytics to do feature extraction. So Sarah, let me switch this over to you and make you the presenter.
Thanks, Kurt. So in this demo, I'll show you how to use machine learning classification to extract features from multispectral imagery. And then we're going to use those classification outputs in additional analyses after that. For this example today, we'll identify impervious surfaces like roads, roofs, and sidewalks. Many state DOTs use impervious surfaces to calculate things like the stormwater bill for a property or identify wetlands areas during development. So we'll be using an object-oriented feature extraction method and the ArcGIS Pro classification tools to accomplish this. Here we have a multispectral image just outside of Louisville, Kentucky, which was provided by the Louisville and Jefferson County Information Consortium. An image like this is ideal for performing detailed feature extraction of impervious surfaces. It's a 6-inch resolution aerial orthophotograph, and it contains a near-infrared band. So we'll zoom into our area of interest, and we can change the band combination to highlight certain features like vegetation and roads. A color infrared band combination makes it easy to pick out the vegetated areas in this neighborhood. So now we can begin the object-based classification process. Object-based classification uses segmented images rather than classifying individual pixels. Segmentation is the process where pixels that are close together and have similar spectral characteristics are grouped into a segment. And segments exhibiting certain shapes and spectral and spatial characteristics can be further grouped into objects. During this classification process, we'll be classifying the segments, not the pixels. To create our segmented image, we'll use the segmentation tool in our classification tools menu. For spectral detail, a higher value will equate to more segments. And for spatial detail, smaller values will create spatially smoother outputs. And the minimum segment size in pixels should be set higher for higher resolution data. Now that we have our segmented image, we can create training samples over features in the image. We'll collect impervious features like roofs, driveways, and roads, as well as pervious features like trees, grass, and exposed dirt. We'll use the Training Sample Manager to create and save our training samples. The Training Samples Manager pane will open with a default classification schema. For this project, we've created our own. In other projects, if you don't already have a classification schema, you can create one using pre-existing training samples, import commonly used schema, or create one manually. We'll load our classification schema along with some previously collected training samples that we can add to. Once we're done loading our classification schema, we'll import the training samples that we've already collected. Now that we've loaded both our classification schema and our training samples, we can begin to collect additional training data. So let's start with some shingle roofs. We'll be using the segment picker tool to select whole segments for our training data, rather than drawing polygons manually. We'll be using our new segmented image as our selection layer, so we'll set that in the segment picker menu here. When you use the segment picker tool, one click will select the shape. For the best results, we recommend that you zoom in closely when you're using this tool because the segments are drawn at the screen resolution. So here we'll select a roof segment, and at this resolution, it appears that the outline matches the segment boundary. But if we zoom into a higher resolution, we'll notice that the outline doesn't really match the outline of the segment very well. So if we click this segment again, now we have two different lines outlining the roof. And if you look closely, you'll see the second selection better matches the outline of the segment. So we can delete this first sample we collected in our Training Sample Manager. Samples are added to this list in the order that you create them. So the first of those two shingle roof samples at the bottom of the list is the one that doesn't match the outline correctly and needs to be deleted. So we'll select in the Training Sample Manager, and then we click the delete icon. And every shape that you draw goes in as a separate class, but you can merge the classes together in the Training Samples Manager pane. So here we have the shingle roof sample we just collected, and we'll select that, and then also select the previously collected shingle roof samples, and then click the collapse tool to merge them together into one class. Once you've finished collecting your training samples, you'll need to save them to use in your classification step. We'll save them using the Save As icon at the top of your training samples list. For today, we have a complete training sample set to save time, so I don't need to save these changes, but if you're doing this yourself at your office, you'd need to save your samples before you move on. Now that we've created our segmented image and we have our training samples, we have the required inputs to classify our image. For our classification, we'll use the image classification tool. We'll be using a support vector machine or an SVM classifier to analyze the data and help recognize patterns in our data set. We'll input our training samples that were already collected earlier. And since we didn't make more than 500 training samples, we'll just keep the default value of 500 for maximum number of samples per class. And this will make sure that we use all the training samples when we're working with our data set. We'll input our segmented image that we made earlier, and we'll check on all the attributes to use in our classification. And once we have our input set, we can run the classifier. Now we have our classified image, and we can then reclassify it into only pervious and impervious surfaces. Since what this DOT really wants to know here is what percentage of each property is covered with impervious surfaces. We'll reclassify using the Reclassify Geoprocessing tool. We'll use our classified data set as the input, and we'll reclassify it based on the class names. And here we'll set all the impervious features to a new value of 1. And then we'll change all the pervious features to no data. And this will give us a new data set that will show only the impervious features. So now we have it, but let's change the symbology so we can view the impervious layer over the imagery a little better. To determine the area of impervious surfaces in each parcel, we'll first need to add the parcel data, which was provided by the county, to our map. Now that we have that parcel data in our map, we'll use the tabulate area geoprocessing tool to calculate the square footage of impervious surfaces in each parcel. The input raster is that parcel layer that we just added to the map, and we'll calculate this using the parcel ID. And we'll use our impervious classified data set to calculate the area of impervious surfaces in each parcel. So the tabulate area tool just created a new table that's been added to our map, and this contains the square footage of impervious surfaces in each parcel. Now you can see each parcel ID is associated with an impervious value in square feet. And this table could be used by itself to determine the stormwater bill for each parcel, but we can also join this table to the parcel feature class itself, which will provide a lot more display options. So we'll join the new table with the parcel layer by the parcel ID. And to make it easier to compare the amount of impervious surfaces from one parcel to another, we'll calculate the percentage of each parcel that includes impervious surfaces. So we'll open our attribute table here, and we'll add a field to the parcel attribute table for the percent of each parcel that is impervious. And for number format, we'll want this displayed as a percentage. When we return back to the parcel attribute table, we can see that our new percent impervious field is now included in that table. Now that we've created this new field, we can calculate the percentage of each parcel that is covered with impervious surfaces using the calculate field tool. For our equation, we'll use the impervious features, which is the shingle roofs, tin roofs, roads, driveways, sidewalks field. That's an automatic name. And we'll divide that by the parcel area. And we'll multiply it by 100 to get a percentage. And once we have our input set, we can run our calculator. And you can see our percent impervious field just updated to include our newly calculated values. Parcels that have no impervious surfaces, like this one here, will have a null value still. To get a better view of the amount of impervious surfaces in each parcel, we can change the parcel layer symbology to reflect this new field you just calculated. And here we have our final map, which shows the percent of each parcel that contains impervious surfaces. Parcels with a lot of them are shown in red, and parcels that have very little impervious surfaces and are mostly something like woods or fields are shown in darker greens. And that's it for me. Back to you, Kurt.
Excellent. Thank you, Sarah. That was terrific. You know, for those of you who looked at that, maybe the DOT isn't so much interested in parcels, but this, of course, could be used with any type of watershed information and be used to calculate the total runoff of any given area. So now I'm going to switch over to Mark Romero, and Mark's going to talk to us about our latest capability, and that is doing drone to map with our Enterprise Edition. So go ahead, Mark.
Okay, thanks, Kurt. So I'm going to start off with a slide that describes this brand new product, Drone to Map Enterprise. One thing to note is this is a complete turnkey solution for generating GIS-ready drone products. It's a complete SaaS offering, which means it operates on the web, and there's some advantages to that. So what's included in the bundle is flight management software. So this lets you insert certain flight collection patterns. And so we're showing one example here, and I'll talk more about that. Once you've inserted those and you've uploaded your photos to the product itself, working in the web has some advantages. First of all, it's going to scale, so you can throw a lot of images at it and not worry about having to worry about your own software hardware capabilities. This is going to use all the capabilities and power of the cloud to generate your products. Because also it's web-based, it's going to simplify the workflow, and there's no system configuration or requirements when working in the cloud. As Kurt said, we've improved our model for generating 3D meshes and point clouds. And then also because it's part of a SaaS offering, it's going to allow you to work with other capabilities and apps that are already part of ArcGIS Online. And just like any of our Esri products, you can use even the desktop software or any of the other ones seen here as a client to work with the data. Here are the typical flight patterns that you would see as a drone operator to capture certain types of GIS features. So the pattern on the left, this is often called a lawnmower pattern or mowing the grass pattern. This is where the drone flies up, takes photos, and then flies back down. And those red points indicate where the drone is taking a photo. One of the important aspects of a flight pattern like this is that you have a sufficient amount of overlap. And these little white squares represent both the front, back, and the side-to-side overlap. And so this is a typical pattern for generating orthomosaics and DSMs. The next one is called a hatch pattern. And so this is a pattern that's typically flown if you want to generate some 3D models over an area of interest. And so similar to the mowing the grass pattern, it flies up and back, and then there's also a side-to-side overlap. So you generate quite a bit of overlap with the hatch pattern. Moving over to the right, another pattern that is typically flown for generating 3D models is an orbital pattern. And so this is when you're typically flying over a single object of interest, like a building. And we often recommend that you have 1 to 3 heights above ground to capture as much as you can of that object. And then finally, one that's introduced to this new product that we haven't seen in Drone to Map is the panorama. And so this is a pattern where you set the drone to fly up at a certain altitude or certain height above ground. The drone is then fixed in that single point, and then it takes a 360-degree panorama view of that area of interest. And I'll be demoing these in a bit. So I'm going to jump right into the demo. Here's a screenshot of the user interface. Okay, so to start a brand new project in Drone to Map Enterprise, you simply click New Project. You give it a name, set the units, in this case meters, and it's wizard-based, so you hit Next. You enter the name of an area of interest. That zooms into your area of interest. You can go ahead and set that as well if you have the lat long, and then hit Next. And you can also add other members of your team to join this project. And that's it. The next step is to create a new flight. So the nice part of this capability is you have one project, but you may want to fly that same area of interest over and over, maybe weekly or monthly. And so with Drone to Map Enterprise, there's a nice user interface for managing all your different flights all in one project. So I'll select New Flight. I'll also give that a name. You can put a date and then hit Next. And then simply select your photos. You can select as many as you want. Just select a couple here. That'll begin the upload process. Optionally, you can check mark this box to process it automatically if you want. So I'll go ahead and save that. And that'll begin the upload process. And then at this point, after I've ingested my photos, I can start working with those immediately. So you can see that the clear circles represent where the drone has collected photos. I can interact with those by clicking that and view the raw source imagery. I can expand that image to get a better view of that image itself. and I can sift through each one of the images to inspect before I kick off the process. So once I'm done looking at the photos, if I have ground control points, I can also ingest those ground control points. In this example, this was taken from an EB with an RTK built into it. So we can ensure that we've already got accurate collection of these photos. So there's no need for GCP in this example. So once I'm ready to process, I can go into the settings. I can tell the system what I want built. So I'm going to choose orthomosaic. I'm going to create a point cloud with medium density. And if I want a mesh, I can also select that here, either standard or high resolution. I can also choose some of the formats that I want to generate of the mesh and click the process button. Once that kicks off, that'll happen all in the cloud. It'll use the resources in the cloud, and then when it's done, it'll send you an email to notify you that your process is complete. So I've already ran this, and so let's check out some of the products that we've generated. So here we're looking at the orthomosaic. We'll zoom in just to give you a sense of the resolution and the behavior and some of that, how it behaves and also processes here in the cloud. I can also view the elevation model. So here's the elevation model. I can query by elevation range directly in the viewer itself. So if I'm interested in a certain range of elevation, I can do that right in the user interface as well. I can choose to build contours as well. And we also have a built-in cut and fill operation that I can interact with right in the view itself. And then finally, I can view the hillshade if I want to here. So once the data is processed, because it's already in the cloud, this just opens up a whole nother set of capabilities that are built into ArcGIS Online. So I put together a couple simple apps. This one's just a simple comparison of the orthomosaic as well as the digital surface model. And so as I move one panel around, I get that same view on the other side. I can move these windows around just to get focus on one of the products. Or I can fully expand any one of these at any point. So that's a simple viewer. I can also bring in a swipe tool that lets me compare one of my older flights to one of my newer flights. And then also we have the ability to work with the point cloud directly in the scene view. Brian's going to talk more about this, so I'm not going to go into detail about it. But just so you know, this is a spec that we passed through OGC called I3S. This allows us to generate all kinds of 3D content and view it in a web browser with really good performance. And so I'm going to toggle between the elevation values and the color values of that point cloud. Okay, so with Drone to Map Enterprise, I did mention that we have a panoramic view. And so this is a setting that's part of the flight management part of the product. And so I just want to demonstrate what that panoramic view looks like. And so this is very simple. In the flight planning software, you just tell the drone to fly straight up at an altitude of your choice. And it flies in a fixed point, and it'll collect a variety of different photos. And keep in mind, these are just still photos, and it's performing the stitching of all those photos and generating this, what appears to be a panoramic seamlessly stitched product. Okay, that's going to conclude my demo. Kurt, I'm going to turn it back over to you.
Excellent, thanks, Mark. That was great, and very exciting new product that we're happy to start rolling out that should really increase your efficiency in your production. So now let's go ahead and turn it over to Brian, and Brian's going to talk a little bit more in detail about how to work with and manage those point clouds. So go ahead, Brian.
Okay, thanks, Kurt. So the goal of this demo is to give you some ideas for maximizing the use of your LiDAR data. It's try to get you to how to manage it, perform analytics with it, and then extract information from it. Many users that have LiDAR data, the end goal is to generate derivative products. So here I'm just showing the building footprints along with roads that were extracted from this LiDAR data. Feature extraction is useful for identifying and managing assets. You could also derive elevation products. Here I'm comparing the digital terrain model or the bare earth surface with the digital surface model or everything above ground. High resolution surface models like these are important for change detection, hydrologic analyses, engineering projects, and so on. Using these derived products, we can then create 3D representations of your town, such as the buildings and trees, allowing us to model an entire city in 3D. To generate some of these products, we first need to organize and manage LiDAR data. Then we can inspect the data and begin our analyses. ArcGIS Pro is the tool for these workflows. In ArcGIS Pro, you can work directly with the raw LAS file. You can begin visualizing your LiDAR data using different renderings to display elevation, classification, surface models, and so on. If you have more than one LAS file, you can load multiple files into a data model we call the LAS dataset. Creating a LAS dataset is straightforward. I just right-click on a folder, create the new LAS dataset, give it a name, and then begin to add the LAS files. Once the LiDAR data is added to the LAS dataset, you can then immediately view various statistics and other information about your LiDAR data, such as the classification, point spacing, its version, total count, and so on. I'll go ahead and add the LAS dataset into the map to begin working with it. The extent of the LAS dataset is seen here with each red square representing each LAS file. With the LAS dataset, we can start to work on all of our LAS files simultaneously. And to do feature extraction, it's important to have a classified point cloud. So I'll speed through the process of the classification, but all the classification tools can be accessed from the classification ribbon. So I'll begin classifying ground. That's what you're seeing in brown here. There are tools that help classify noise and overlap, so you can clean up unwanted points. Next, I'll do the buildings and then trees. You can use predefined features to help us classify point clouds. So if you have access to planimetric data, such as road surfaces, building footprints, you could use these features to help you classify your data. Switching to 3D allows you to more easily visualize and inspect how the classification process is going. These automated tools are never perfect. Sometimes you may need to go back and manually classify certain features, such as this bridge deck. It was incorrectly identified as a building. So using the manual classification tool to select specific points to classify, you can fix those problems. You'll notice how I accidentally selected some ground points here. Well, there's a tool to help you isolate your point cloud. It's called the profile tool. And using this will help you ensure that only the returns that you want to be considered a bridge deck are classified as such. Switching gears now, I'll show you how to begin creating surface models from a point cloud. So once your LiDAR data is classified, you can create specific surface products by using the LAS dataset to Raster geoprocessing tool. For example, I'll first use the tool to create a first return digital surface model. We can then filter our LAS dataset by using the LAS filter to turn off everything but the ground and LAS returns. Doing this step isolates only those returns, so that when we run the tool again, we are now creating a digital terrain model or bare earth surface. Using raster functions within the imagery ribbon, we can immediately generate hillshades, slopes, aspects, contours. We could do raster math and so on. Here, I'll be creating a hillshade representation for our DSM and DTM surface models on the fly by using these raster functions. If I were then to manage these data in a mosaic data set, I can apply these raster functions as processing templates and share these elevation models and derivative products within my organization. Let's go back and create one more raster from the LiDAR. This time, instead of elevation, I'm going to make an intensity raster. Intensity from LiDAR provides information on signal strength of the LiDAR pulse and is tied to the reflectivity of the surface. A lot of useful information can be extracted from the intensity raster. Notice how the vegetation and pervious surfaces look dark in this image, indicating low reflectivity. I want to be able to isolate information like the road network. So using the filter tool again, I'm going to filter out all the vegetation, buildings, and noise from the LiDAR. I'm also going to choose first returns only. Then I'll rerun the LAS dataset to raster tool to recreate that intensity raster. Running this tool again produces a product that can be used to help isolate the roads. Next, I'll simply use a raster function for binary threshold to generate a binary raster. And then I'll mask out the relatively high reflective areas to be by changing everything else to no data. This leaves me with the road network in raster form. Turning off the binary threshold, we can see how that road network did. And after some cleanup, you can convert this to a polygon and create a road network. So the next part of this demo, I'll introduce how to enable your LiDAR data to create 3D scenes. We do this using the local government 3D base map solution. This solution provides a series of tasks that walk you through the entire process, from classifying LiDAR, creating necessary surface products, and extracting the roof forms. Publishing these data into a web scene like Mark showed you earlier opens up more possibilities for sharing your LiDAR and 3D data. Here I'm just showing a simple web application to compare the classified point cloud to the 3D buildings. This app is one of the many pre-configured applications that can be created using ArcGIS Online. So we can run simple measure tools and the like. Large point cloud scene layer packages can be loaded into a web scene for further analysis and visualization. Here's a project one of my colleagues put together to model potential future drone delivery corridors. The point of this is to show ways to work with features and point clouds in a web application. As I navigate through this scene, you'll soon visualize where trees encroach into the corridor. Tools like these allow for crews to give them a simple solution to monitor and manage these areas so that they can combat vegetation encroachment and anything else they need to monitor. So this wraps up my demo. I hope it inspired you to find new ways to work with your LiDAR data. Back to you, Kurt.
Kurt, are you on mute or?
Hello, can you hear me now? Sorry about that.
Yeah.
I lost control of where my mute button was. Anyway, sorry about that, folks. Let's go ahead and now switch it over to Amin. Amin's going to talk about using AI technology to go ahead and do feature extraction out of point clouds. So Amin, I need to make you the presenter. Go ahead, Terry, if you could make Amin the presenter, that'd be great.
Awesome. You guys can see my screen?
We can.
Cool. So today I'm going to mostly talk about, I had colleagues that they talk about LiDAR and other stuff, mostly from feature extraction as well as, like processing the data. But today I'm going to mostly spend some time to talk about our recent project that we had regarding using AI, basically to apply directly to the point cloud. So the conventional approach that we used to have, we didn't have actually good algorithm that can go through the point cloud and extract feature. And most of the things that happen currently is just having operator or technician that sit down in front of computer, go to the LiDAR point cloud directly and try to spot those features, that are important for the Department of Transportation. So today I'm going to show you the recent work that we had with one of the well-known basically railroad company that they were asking us to extract, milepost, signal, and other stuff directly from point cloud. And currently they were doing it manually with over 20 technicians that take them a month to finish that. So when you wrap around your head around point cloud, it's very similar to Imagery, except you are going from 2D to 3D points. So this image, show the application that we have. We can have classification, partial segmentation, as well as semantic segmentation. Classification is just like, you have a box that is a scan, pass it to the computer, and computer tell you what class it belongs. Very simple, just automate the entire things that computer does that. And here, rather than dealing with RGB or some 2D shape, we are actually dealing with 3D, or I would say 3D point cloud that they have exact coordinate like XYZ, intensity, and other stuff that Brian mentioned. So today I'm going to cover two projects that we had. One of them was classification, and another one was semantic segmentation. And these are very different. Classification, you only say the class. Segmentation, you actually build a model to label every single point. We are talking about million points in one scene that you want to label them with the model, which is pretty massive. So the project that we had with one of the railroad company, they were asking us, can you go over tons of miles of the point cloud that I have and actually ask computer to label the location of those assets that we are interested in. The asset that they were looking for was signal. They can come in different form. I have the point cloud on the left side and actual shape and actually in real world that how it looked like. And you can see that in point cloud is actually color coded with elevation. They were looking for milepost, which is the lower one that basically it's like 2 meters tall. It shows that the mileage that we have. And when you look at it, it's just massive data that is really even hard to identify them. The other one is crossing, that it's actually stop the cars when the train comes. I'm sure you have seen it on the road. And the last one is switches, that they are even harder. When you go through the point cloud, it's even harder to see them because they are so small and attached to the railroad. So what we basically did, we built a model, and we had different parts. Was data pipeline as well as the model pipeline. So the data pipeline was how we can actually process this data to train the model. And the model that we use for training got called PointNet, that directly digests point cloud. This point cloud, have XYZ as well as intensity. You can add any other description as well to pass it through the model. This model is capable to do either classification or segmentation, and it has close to 3 or 4 million parameters. And what it does is a supervised approach that you feed your input, which is your point cloud, and you have some output that called training data that tell for example, the model, here is the signal, here is basically the crossing, here is the milepost. And after doing that, we build a model for any new location that you have LiDAR data, which are mostly unlabeled. You can pass this model to those and actually extract the location of those assets. So I'm going to walk you through the blog that I have here to basically show. I guess we don't have enough time to go through the processing, but basically what did happen, you are going to have like passively pass each of these boxes to the model, and model is going to tell you, for example, here we have signal. And there are also more going on with data processing, but at the end, we came up with basically this package that in terms of data pipeline, it used most of the functionality regarding ArcGIS that we have. And for data processing, then it goes to the model pipeline that is run on GPU on the cloud. And at the end, what it returns you is actually a feature class on the cloud that shows the location of the asset. So from going to here, I have another application that my colleague did regarding segmentation. So let's say you have a massive data set, you want to label every single point cloud. And PointNet can do that. We also have PointCNN that train the model to identify cables like buildings, roads, and a bunch of other assets. And we are also working on signal and other stuff currently. But what has happened basically when you build a model, it go through the point cloud. Again, it's a supervised approach. It get the input, which is your raw input. It just doesn't have any info, as well as your label as output. Very similar to the imagery, have their classes. It can be houses, it could be vegetation, it could be road or other stuff. Then build a model. And after you have the model, you can apply to the new data set, let's say for the entire town, and process them, label them each, and return like a shiny label classified actually LiDAR data. And I have one more to go, and which is more imagery application that we did with Department of Transportation in DC, and we are currently doing it with Department of Transportation in North Carolina, where they ask us to actually monitor traffic flow in DC. So what we basically did, again, we built a model with the deep learning model that called Yellow Tree. It has close to 32 million parameters that, it has different steps. We have live feed camera, we have like camera at intersection that send images to our model, which is trained, is fully deployed on the cloud. And after the image comes, we extract those objects like cars, pedestrian, trucks, buses, and everything. And after we extract those objects, we send those info as a JSON to the geo event, which is another piece that we have. And it's a real-time processing and a storage unit that you can use actually to push the data there. And besides that, we have operation dashboard that user can actually zoom into those different locations to see what's happening in DC. So I can show you one of the actually dashboard that we have. So these are actually the data that is sending live to the demo and to the dashboard. And when you are like basically load the dashboard, you can see what's happening at different intersection in DC. So you can click, zoom in, zoom out to see what's happening. We have some basic statistic regarding the number of the cars, bicycle, and everything. We are actually storing the images, for different time of the day. This is running live currently, and we do also anomaly detection to find abnormal behavior at different intersection. Let's say, if the volume of the car or changes across time with comparing with historical data, or even some abnormal behavior from pedestrian, they are just going to some location that they shouldn't. So having all of these, you can actually leverage this data. These are, this panel actually updated based on the study area or extent. And here is mostly anomaly detection that, it just pop out as a red dot on the map that shows where are those anomaly happening. You can actually zoom and see where are those location. And yep, I guess that's pretty much it, Kurt, for me, because we want to have enough time for questions.
Okay, so thank you, Amin. I appreciate that. What Amin's doing is very powerful stuff with that whole AI extraction. Amin, is it possible for you to share the links to your blog site so if people want to read more detail about, the extraction you're doing from the point clouds and stuff, that they can have access to that?
Yep, definitely. I have them online actually. We have them on Medium. We can share everything.
Okay.
So
we'll get those over to Terry.
Yeah,
go ahead,
if you
Terry.
send those, we'll include those in the slides that go up on the GeoNet today. So, all right, we have a few minutes for questions, and so we'll go ahead and take some questions. Let's see, I think there's one. Does Drone to Map Enterprise consume ArcGIS Online credits? Is the question.
I'll go ahead and answer that one. The answer on that right now is no. It is going to be a SaaS offering that is paid for on an annual subscription basis. So right now, there's not a plan to incorporate credits in there. Depending on how things go, that might change in the future because it's a brand new product. But as of right now, it is not a credit-consuming capability. It is a subscription-based capability.
Okay, and Kurt, this one's probably for you. It really had to do with when you were actually showing the oblique imagery option. Someone asked the question whether that would actually work with eagle view pictometry. You have
Absolutely.
An answer.
Yep. That's one of the packages, one of the imagery solutions that we built it for. Like we said, a real weakness with desktop before was its inability to work good with obliques, and we're working very hard to change that inside of Pro. And Eagle View Pictometry is one of our key partners that we want to make sure we support, so they're definitely included in that mix.
Okay, and I mean, this is probably the question for you. Really has to do any use of Amazon Deep View in your work?
Deep View, no, but we are using that deep learning instance that Amazon has to basically train the model on GPUs. And we also use Azure for, they have deep learning instances over there that we are currently leveraging for training our models with massive data set.
Okay, and another, Sarah, this was probably more for you. Can the segmentation process be used to create building footprints?
Yep, definitely. We have already done that with a bunch of countries in Europe. We did with Netherlands, we did with Switzerland. I think we did with one other country as well.
Okay. And then what is the accuracy of the extracted features from the machine learning?
For classification that I show for railroad, we could successfully detect signal, crossing, as well as mileposts with over 80% accuracy, both for precision and recall. For segmentation, it was even better. I think we have over 90% accuracy for building footprint extraction using LiDAR.
Okay, and let's see, Kurt, maybe for this is, have we tried using near map imagery, I guess is the question.
Yeah, Nearmap is another one of our key partners, and we use Nearmap. We can consume Nearmap across the board. We're also working with them to actually provide raw photogrammetric sources to use to do more automated feature extraction. So not just their imagery service, but actually getting access to their raw imagery as well. But yes, Nearmap's a key partner of ours.
Okay, that's great. Well, I think we've run out of time for today. We'd like to thank all of you for attending. As we mentioned, the slides will be available on the GeoNet Departments of Transportation. Please feel free to reach out if you have additional questions. We'll be happy to answer those. And again, thanks for attending, and we look forward to seeing you at future DOT webinars. Okay, thank you. Bye-bye.